Quantum mechanics requires that the total probability of finding a particle across all space remains exactly 1 as the system evolves. If a quantum state were represented by a single real number, its rate of change would be directly proportional to its current value. Real-valued first-order differential equations typically describe diffusion or decay, where information and density dissipate into the environment over time. To preserve the probability norm, the change in the wave function must always be perpendicular to the wave function itself in its state space. Multiplying a value by the imaginary unit I represents a 90-degree rotation in the complex plane, providing that necessary perpendicular direction. The Schrodinger equation places the imaginary unit I next to the time derivative to ensure the evolution is a rotation, not a scaling.
Because the wave function is complex, it possesses both a magnitude and a phase, which are essential for the phenomenon of quantum interference. Interference occurs when two complex amplitudes add together, potentially canceling out if their phases are 180 degrees apart. Time evolution in quantum mechanics is unitary, meaning it is a transformation that preserves the inner product and the norm of vectors. The Hamiltonian operator represents the total energy and acts as the generator of time translation through the imaginary unit I. For the evolution to remain unitary, the Hamiltonian must be Hermitian, ensuring that all energy eigenvalues are strictly real numbers. The rate at which the phase of a wave function rotates in the complex plane is directly proportional to the energy of that state. Euler's formula connects the complex exponential used in the Schrodinger equation to trigonometric oscillations of sines and cosines.
Without the imaginary unit, the solutions would be exponential growth or decay rather than the stable oscillations seen in atomic orbits. The imaginary unit allows for the derivation of a local continuity equation, where the change in probability density equals the divergence of current. The probability current is proportional to the gradient of the phase, proving that the phase carries physical information about particle motion. While the wave function is complex, the observable probability is the square of its magnitude, which is always a non-negative real number. Calculating the probability density requires multiplying the wave function by its complex conjugate, which effectively cancels out the phase component. A moving wave packet is a superposition of complex waves with different phases, resulting in a localized envelope that moves through space.
The dispersion of the wave packet occurs because different frequency components have phases that rotate at different speeds in the complex plane. During quantum tunneling, the wave function inside the barrier becomes an evanescent wave, yet it retains phase information that affects the transmission. In stationary states, the probability density is constant in time because the complex phase rotation does not change the vector magnitude. Although the phase of a single wave function is not directly observable, the relative phase between two states determines their physical interaction. The invariance of the system under global phase shifts leads directly to the conservation of electric charge through Noether's theorem. The need for complex numbers persists in relativistic quantum mechanics, where the Dirac equation describes particles with spin using complex spinors. Feynman's path integral formulation sums complex phase factors along every possible path to calculate the final probability amplitude of an event. Classical paths emerge when the phases of nearby paths constructively interfere, which happens at the minimum of the classical action. The state space of a quantum system is a complex Hilbert space, where the geometry is defined by a complex inner product. Linearity in this complex space allows for the superposition of multiple physical states, which is the foundation of quantum computing algorithms. Quantum gates are simply unitary operators that rotate a qubit state in the complex plane to perform logical operations. Entanglement involves complex correlations where the phase relationship between two particles is locked across long distances. Without the imaginary unit, the geometry of quantum mechanics would collapse, making it impossible to represent circular or periodic motion. During measurement, the complex wave function projects onto a specific real-valued eigenstate, causing the loss of original phase information.
Decoherence occurs when environmental interactions randomize the phase, effectively turning a quantum superposition into a classical probability distribution. In some advanced physics models, replacing real time with imaginary time transforms the Schrodinger equation into a statistical partition function. This wick rotation allows physicists to use techniques from Euclidean geometry to solve complex problems in quantum field theory. Complex analysis provides powerful tools like contour integration to calculate scattering amplitudes and particle lifetimes in high-energy physics. Physical resonances in particle accelerators are mathematically identified as poles in the complex energy plane, describing short-lived particles. Analytic continuation allows us to understand physical behavior in regimes that are not directly accessible through standard real variables. Modern research explores non-Hermitian Hamiltonians with parity time symmetry, which can still have real energy spectra despite gain and loss.
In these non-Hermitian systems, unique singularities called exceptional points appear, where both eigenvalues and eigenvectors coincide in the complex plane. Understanding these complex phase dynamics is what enables the development of laser technology, semiconductors, and MRI scanners. While once considered purely imaginary, these numbers are the most accurate way to describe the fundamental structure of our physical reality. The imaginary unit I remains the mathematical anchor that keeps the laws of physics from dissolving into nothingness by anchoring probability to the unit circle.